You know that incredible shimmer on a butterfly's wing? Or the idea of windows that can intelligently block out heat all on their own? Well, the secret to that stuff lies in a technology that promises a future full of perfect, super smart materials. But, and this is a big but, this amazing tool comes with a serious catch.
Just imagine for a second a world where surfaces are way more than they seem. Think about a phone screen that is literally almost impossible to scratch. Or a building that shimmers and changes color depending on how the sun hits it. This isn't science fiction, you know? It's the incredible potential of a process called chemical vapor deposition, or CVD for short. So first, let's look at the dream scenario. We're going to dive into the incredible promise of CVD and see what makes it so revolutionary, at least on paper. Okay, so what is chemical vapor deposition? The best way to picture it is like an atomic paintbrush. I'm serious. You take a surface, what scientists call a substrate, and you put it inside a special chamber. Then you introduce some very specific gases. Those gases react and start to deposit this incredibly thin film on the surface, building it up one single atom at a time. It is precision engineering at its most extreme. And the key here, the real magic, is the scale we're talking about. Because CVD works at the nanometer level, it lets us engineer surfaces with properties that are just impossible to get any other way. We can fine-tune exactly how light interacts with a surface, or we can make it unbelievably durable and tough. And the results of all this precision? They're pretty remarkable. You get these coatings that are perfectly uniform, even over big, weirdly shaped areas. This nanoscale control lets you create things like structural color, which is exactly how those butterfly wings get their shimmer without any ink or pigment. It's all about the texture. This leads to amazing protective qualities and opens the door for futuristic tech like smart windows that can tint on demand. The potential is just massive. All of which sounds amazing, right? Almost too good to be true. But this is where the story kind of takes a turn. And we have to ask the really obvious question. Yeah, if we can make these perfect high-tech surfaces, why isn't your car covered in a scratch-proof, color-shifting film? Why isn't every building using these energy-saving smart windows? Well, it turns out that creating perfection on an atomic scale is, well, it's really, really complicated. Turns out there are 4 major hurdles standing between CVD's potential and it being used everywhere. And understanding these roadblocks is really the key to seeing the real-world limits of this otherwise incredible process. The first one, and you could argue it's the biggest, is just simple economics. CVD is an incredibly demanding process, which makes it both super complex and very, very expensive. Let's break that down a bit. To do this, you need really high temperatures in a vacuum-sealed chamber. That means you need specialized equipment that just guzzles energy. Then, the gases you use are often hazardous, so you need highly skilled operators and super strict safety rules. All of that complexity makes trying to scale it up for mass production an absolute financial and logistical nightmare. Okay, so let's say you have deep pockets and you can afford the process. Now you smash right into the next problem, making the coating actually stick. It's a really basic physics challenge. The whole goal is to create this perfect, strong bond between the new film and the original surface. But here's the problem. CVD is a hot process. So you're laying down this hot film onto a much cooler surface, especially something like plastic. And they expand and contract at totally different rates. This thermal mismatch creates a ton of stress, and the coating can just peel, crack, or pop right off. Think of it like trying to glue something that just came out of the oven onto a block of ice. That bond is under stress from the very beginning. Next up, hurdle number 3, maintaining perfection. When you're building something atom by atom, your margin for error is pretty much 0. The tiniest little inconsistency can ruin the whole thing. Getting that perfectly uniform film is a constant fight. For starters, if the original surface isn't perfectly smooth, the coating won't be either. And then, the process is so ridiculously sensitive. The smallest fluctuation in the gas flow or the temperature can wreck the delicate optical properties you're trying to create. That means you have to monitor the entire process constantly, which, you guessed it, just adds even more complexity and cost. And finally, that brings us to hurdle number 4, the environmental and safety footprint. Building these perfect surfaces, it turns out, can be a pretty messy business. The entire life cycle of CVD is a challenge. You start with hazardous materials, those toxic gases we mentioned. Then the chemical reaction itself creates even more toxic byproducts. All of that waste has to be managed and disposed of really carefully and expensively. And on top of it all, you have to navigate a jungle of safety and environmental regulations. It's just another huge barrier.
So, when you add up all these challenges, the cost, the adhesion problems, the insane quality control, the environmental impact, a very clear picture starts to emerge.
And that picture is this. For now, CVD is a tool for a very select few. We're talking about high-value industries like aerospace or high-end electronics or specialized medical devices, fields where the performance is absolutely critical and the cost is a secondary concern. It's just not a tool for our everyday consumer goods.
The source material we've been digging into really sums it up perfectly. It says, economic and technical constraints impede its broad implementation. And that's the core conflict of CVD, isn't it? It's a technology that can create near-perfect surfaces, but is held back by the very real-world challenges of actually making it happen. This leaves us with a fascinating question for the future. If CVD is this powerful but impractical double-edged sword, what comes next? What alternative methods are scientists and engineers cooking up to finally bring the promise of these incredible smart surfaces out of the high-tech lab and into our daily lives?